Good afternoon. My task is wake you up from the after lunch dreams. I will try my best. Tempest, it's a rather old phenomenon, and I would like to talk with the new aspects of the tempest. Let's start from the stove. It's a very nice Hungarian idiom, means you have to begin at the beginning. So I would like to steal data. I would like to steal unencrypted, easy available data. And I would like to remain in the background without any consequences. So I would like to find sources for unencrypted data. Which sources can I identify? The first is the screen. The second one, the keyboard and mouse. Mouse is not so important. Maybe something else, the printer. If I want to print something, I have to send it to the printer, and I cannot use any encryption because printers are unable to decrypt it. If I use, for example, a print server, the situation will be slightly different because between my machine and the print server, the traffic can be encrypted, but from the server to the printer, that USB 2 line must be unencrypted. Can I catch it? I don't know. If I cannot have physical access to the machine, I have to convince the machine to emanate the data, to radiate the data, and somehow I have to capture it. Which parts of the machine can emanate data? External networks, cables, plugs, printed circuit boards, and the screens. External components. Wi-Fi is a well-known problem. WiMAX is a bit better. Bluetooth not so important because a very small amount of data is running on Bluetooth connections. Broadband over power line is an interesting question because in some countries it's a very high heap of the BOP, and sometimes it can result unexpected effects. I would like to show some. This is a New Zealand clip from a radio amateur station.
Broadband over power lines is yet another technology to enable the delivery of high-speed data services over the power distribution system. And this video gives an audible and visual demonstration of this technology's potential for interference to the high-frequency radio spectrum. It is currently being trialled in North Hobart, which is a suburb of the capital city of Hobart. We're heading over Burnett Street traffic lights along Argyle Street in a northerly direction, and we are about to enter the North Hobart BPL trial area. In this video I am using standard mobile amateur radio equipment, and no audio or video manipulation has been used. The signal meter superimposed at the top of the screen provides an indication of signal strength that is being received on the 80-metre amateur band. Mid-range on this signal meter is what amateurs call an S9 signal strength, and this is a very high signal level. The BPL interference that can now be heard is consistently above the S9 level throughout the North Hobart BPL trial area, as this video will demonstrate. This BPL trial is being run by Aurora Energy, the local power retailer, and its telecommunication arm Tastel. The BPL system used in this trial is manufactured by Mitsubishi, and it utilises the DS2 BPL chipset. We turn into Ryde Street past the North Hobart Football Oval, and the BPL interference level continues well above the extreme S9 level. Radio amateurs, or hams, are licensed users of certain parts of the radio spectrum who have passed assessments regulated by the Australian Communications and Media Authority to prove competency in operating radio equipment.
So, As you could hear, your data were emanated on a broadband line, and you only have to capture that signal and decrypt it, and you have all of the data processed. Cable networks, it's not so interesting for us because mostly shielded, mostly twisted, mostly transfer encrypted data, so I don't want to deal with it because it's too hard to hack it. Keyboard, unencrypted signal, but not too much data, but I can capture user IDs, passwords, so maybe it can be interesting. Plugs. This is a military computer with shielded plugs, and very small active surface is available, so not so hopeful to get any signal from this machine. Printed circuit board. Hard to select the appropriate signal because there is a chaotic mixture of different electronic signals. So maybe we should focus on the USB cable. USB cable is important because when I send data to a printer, I must send unencrypted data. The only problem is when the USB standards were established, the developers was thinking about the electromagnetic emanation. That means that they built a so-called slew rate control into the circuits. I try to explain it. The normal USB 2 signal is something like that on the corner. It seems to be a rather clear signal, but due to the slew rate control, it's not a square wave signal anymore. It's almost sinusoidal. That means that I will not have harmonics. I only will have the basic signal, so it will be hard to capture it. Maybe next year. But the display was radiating, and it was discovered very soon. And it got a code name, the Tempest. Tempest means there was a very simple configuration from Wimfanek. The radiation of the screen can be captured with an antenna, can be amplified and sent to a normal TV. And the TV screen will show the same picture as my monitor, though it will be monochromic. How does it work? In the monitor, we have an electron gun, and the electronic beam will start from the gun and will be accelerated, deflected, and will be hit the screen. During this run, the electron beam means a definite current, and that current will result in electromagnetic emanation. The beam will visit pixel by pixel the whole screen. Finally, at the end of a line, it will run back, and at the end of the screen, there will be a longer flyback signal. And these effects make easy to synchronize my TV to the monitor. And the antenna, which can emanate the signal, will be the beam itself. So let's give it a try. That was a newer version of the 1EC configuration with a PC and an analog digital converter and so on. So we tried to apply the modern technology to reproduce the picture. The result was something like that. Not so nice, but why? The necessary frequencies to reproduce the picture pixel by pixel can be seen here. It's a very, very, very high frequency, and our equipment may not be able to do that. For example, if I connect it to the PC, the fastest part of the external connections were the line printer parallel interface, and it was too slow. You can see the maximal speed was 500 kilosamples. It's about 5 megabit per second. And the radio side was much more critical because the bandwidth of the radio significantly slower than the necessary transfer rate. In the reality, the situation is a bit more worse because if you can see a simple, very simple black and white screen shows that the current swings about 3 times higher frequency than the pixel frequency. It's a very important thing because we will find something very similar at the TFT monitors. In this case, the reason for that swinging is the colorfulness, because in the CRT tube there are shadow mask or slot mask or trinitron configuration, but there are 3 separated electronic guns in the tube, and the currents will be summarized. If the pixel current would be a real square wave, we could describe it with the Fourier sequence, and it would show something like this. But in the reality, due to the 3 different color signals, it will be something like this. The basic frequencies almost disappear, and the 3rd, 4th, and 6th harmonics will be higher. So Fourier equation is not usable anymore. This is a radiation chart of some video cards. So if we want to reproduce the screen, we have to use a receiver which is able to cover a fairly wide band from 150 megahertz to 650. It's a very high frequency and very wide bandwidth. PC will be too slow for this procession, and we need a much better radio than a normal communication receiver. And probably we have to use a digital signal processing. What does it mean, a good radio? It has to cover the whole frequency band. It can be a low noise version, sensitive version, and we need a proper output level. The bandwidth is essential, so it's very hard to find something like that. You have to build it, and it needs special instrumentations and practice. The first stage of the radio should mix the signal, the incoming signal, with the local signal, and produce the baseband level. The level was be emanated by the monitor. If I have the baseband signal, I can reproduce the screen. What else should we do? This is the signal. I have orientation points. The blanking signal when the deflection system from the end of the line runs back to the beginning of the next line. In addition, I will have a so-called line sync signal. This will be a high impulse for the deflection system on the receiver side. I will be able to use it to synchronize my other device. And there will be a longer flyback signal after the end of the whole screen. What else can we do? We need a better antenna. Antenna means something which is oriented. The better the orientation of the antenna, more exactly I can target the display from I want to steal the picture. A better radio and high-speed digital signal processing. Those components are available. For example, this configuration can be ordered from the Texas Instruments. It's about $50. But that was only the past, and we thought that the Tempest phenomenon disappeared with the CRT displays. But no. This is a TFT display, as we know, and if we go closer, it seems that every dot is 1 pixel. Right. But every pixel is a TFT array, an array of transistors, something like that. That means that when I write my data to the display, I select a gate line. This gate line will define a row on the display. Then I select the data line one by one. 3 data lines will drive 1 single pixel, the 3 transistors. And the data lines and the gate lines were crossed, that TFT transistors will be excited. This exciter pulse will result a very strong and very well-defined emanation. Have you ever seen something similar? Yes, the DRAMs working on that way, on the column address is about the same as the gate line, and the row address is about the same as the data line. If you turn it with 90 degrees, you can find the same architecture. What does it mean? When I illuminate a color pixel, the appropriate transistor will be excited. Excited means it will draw a fairly high current. That fairly high current will result a very strong impulse. That impulse will be emanated, and the emanated pulse can be captured. The speed range, due to it's very similar to the DRAM, the frequency range also will be the similar, but as we have 3 transistors on 1 pixel, we have to look for the 2nd, 4th, and 6th harmonics, because those will be emanated. So the frequency range is moved from a higher range, and we have to find the signals there. And Tempest is a very critical thing, so there are companies for measuring the Tempest proofness, the level of radiation of the different machines, and the other side we try to hack the Tempest-proof qualified machines. I would like to show you a short demo. I need a playlist. I need some technical help. So you can see a screen with an animated GIF. A very simple printed board antenna, cable, and the box, and another screen which is copies the previous one only in black and white. So the configuration is very simple. We know about everything in this configuration except that flat box on the right hand side. That one. What is that? So, the flat box with the cooling fan is a so-called software-defined radio. A special radio receiver which works very different way as we used to think about radios. Software-defined radio means in the first stage I mix the signal, the incoming signal with the local signal, push it back to the baseband, digitize it, and process with computing methods. That means the whole decryption or demodulation procedure will be done on software way, and it will be controlled via user port or USB port. So this very simple loop radio will be able to do the task without having instrumentation, without having soldering iron. We only have proper control program. It's a bit special because this box is covering the frequency band from 1 kHz to 3 GHz. It's very, very wide band, and it can cover it in one single step. It can recover the baseband, and it can be controlled via USB port. Of course, they had a very good antenna. The antenna itself is that 4 sleeves. The external part is only a mechanic part to position the antenna. And in the head of the antenna there is a preamplifier and a polarization switch. And now we can move the screen away, and we can reproduce it. The picture, of course, will be monochrome. The artificial colors illustrate the signal strength. And the horizontal face of the image has to be corrected manually because the synchronous signals are very weak. In the conventional deflection systems, there was a fairly long flyback delay because the inductance of the deflection system needed it. But in this case, we don't have a long flyback, So it's harder to find the synchron poses. The processing program averaged 10 consecutive frames. The receiving frequency is 1.29 gigahertz. These are the normal controls: contrast, brightness, the offset of the screen, the number of frames averaged. This way, I can reduce the noise, the effect of the noise coming from the receiver side. And you can see the frame frequencies on the target was not exactly the standard. It was a slightly different. And the resolution was very high. Line frequency was not the standard value, but very close to it. But these differences can be compensated manually. So it seems to be a very good tool to capture screens from distance, over walls, windows. So it's a bit dangerous, but it's a very expensive tool. That receiver was about $18,000. That custom-made antenna was about $10,000. The program is free, open source, but for playing hacker, it's a bit pricey tool. Is there something less expensive? Oh, let's watch the TV. If you browse the internet, you can find that DVB-T receivers are not too pricey and available on eBay or anything else. And those are also SDR receivers, especially programmed for DVB-T reception. The price range is between $10 and $20, so not a really high price. And the bandwidth is rather high because one transport stream for DVB-T is 8 megahertz. The modern USB dongles can process up to 8 transport streams. That means 8 times 8, 64 megahertz bandwidth. It's more than enough. In addition, during the manufacturing, the manufacturer have to check every chips. So the DVB-T chip has a so-called test mode. If you can activate the test mode, it will forget the DVB-T standard, the frequency limits, and you can freely program it. So you will have an SDR receiver for $10. You have to select SAW chip, which is able to cover a very wide band. For example, the RTL 2832 is a very good one, and not too expensive because when I bought it, it was $15. This is the dongle itself, and if the bandwidth is not enough or the coverage is not enough, you can add external converters and you can extend the reception band from DC to 3 gigahertz. Then you have to connect it to your PC. In this case, you will have a DVB-T TV receiver. With the remote control, you can use your PC as a TV, but we would like to do something else. There is an open source driver, the Zadig driver which can turn the chipset to test mode. With that driver, your PC can give the reception frequency and the bandwidth for the chipset, and it will work on that way. In addition, you need a good antenna. You can order it from Prague for $10,000, or you can buy on eBay. It's a printed circuit board antenna for $15. For our purpose, is as good as the higher price one. And you have to install a special program which can gives the parameters for the USB dongle and can drive it. One of the most popular ones is the HD SDR program. Now it's working in this frequency range. These are broadcasting stations, and here is the modulation of the station. We can see the band we are receiving, the signal strength, so we can select which is the best one, and we can use now the PC as a radio, not as a TV. We can select the method of the demodulation, AM, FM, digital method, lower sideband, upper sideband, DRM. And there is one more special, the CV. What does it mean, CV? Continuous wave. The radio is radiating continuous signal, and I don't want to deal with the modulation. I need only the signal itself. So I selected an FM radio station. This is the emanated signal. You can see that the wideband signal is coming into the device. We can see the modulation here. There is a fast Fourier transformation of the signal. At present, I don't want to use it, but it shows that every parameter of the radiated signal is available with this simple open source program. Let's talk about the CV. If I select the CV demodulation method, the radio signal will be converted down to the baseband. I will get back the baseband signal. That was my primary aim, to get back the baseband so-called envelope, the coverage of the signal. And from that point, it's only programming, because if you have the baseband signal, you can detect the synchron signals, and you can recover pixel by pixel the original screen, the original picture. From this point of view, if you look at this building, it's an office building. It's a real security nightmare, because I buy an antenna for $15. I buy a preamplifier for $20. I buy a USB dongle for $15. It's about $50 together. I download the proper driver and SDR control program to my machine, and I am sitting in the coffee house and I harvesting your data without any track remaining in the background. It's very hard to discover that something is reading your screen, and I will collect all of your data. So that's the Tempest. Where can I obtain these components? The USB dongle is on eBay. I recommend buying the RTL 2832 because it's very versatile. There is one weak point of these dongles. If you connect an external antenna, the incoming signal will be higher than expected by the developers. And the electrostatic discharge can damage the chipset. In the RTL 2832, there is a protection diode pair on the input, and it can protect the chipset from electrostatic discharges without reducing the sensitivity. Logarithmic periodic antenna. It's also available on eBay. I prefer to buy the so-called asymmetric version because you can use it with a preamplifier. That it's easy to connect it to a preamplifier. You don't have to deal with extra cables, extra transformers, balance transformers, and so on. So you need an asymmetric output antenna. It's between $10 and $20, not a big deal. SDR control programs. The most popular in the radio amateur area, the HD SDR. The other one, I don't prefer it. It's not so convenient that the HD SDR, the SDR Sharp, the name means that it's supported with one company. And ZX driver is open source and available for almost every operating system, from Macintosh to Linux, of course Windows. For Windows users, the ZX driver has a special version for Windows XP because XP works a bit different than other Windowses. So, thank you for your patience. That was my presentation.